Today we're going to talk about finding a line of best fit. Okay, so this covers two standards. It covers the 8th grade integrated algebra standard 8, statistics and probability 2. Know that straight lines are widely used to model relationships between two quantitative variables. Quantitative meaning numerical variables. For scatter plots that suggest a linear association, informally fit a straight line. Okay, that's the line of best fit. And informally assess the model by judging the closeness of the data points to the line. So we're going to talk about how you can make an argument or a statement about how the line fits. Does it fit well? Does it not fit well? Based on the idea of closeness. Okay, so that's the 8th grade standard. In the integrated algebra standard, it's manually construct a reasonable line of best fit for a scatter plot and determine the equation of that line. So that's what we're going to do today. We're going to find not only the line of best fit, but the equation of the line as well. So the only thing that makes the integrated algebra standard a little bit different than the 8th grade standard is that you actually have to find the equation of that line. Okay, we're also going to talk about correlation and causation like we did in the last lesson, and we're going to talk about a regression line. Okay, so a line of best fit is a line that seems to go through the center of the data points. Now, center is an idea that we sort of have to discuss a little bit. The center means that it doesn't necessarily have to go through all the points, or it doesn't actually have to even go through any of them. The line of best fit for the data means that if you added up all the distances of the points from the line, that number is at the minimum in the line of best fit. So that's kind of a confusing way to do it. So let's look at these three examples. Let's talk about 1, 2, and 3. Now, 1 is a line of best fit because it looks like it sort of goes through, so taking into account this right here, you're trying to think of the averages, okay? So in fact, actually, if I'm trying to figure out which one is the best line, the line of best fit, I would have picked number 2. And that's because, look at the blue line right here. It looks like if I measured the distances that these orange points were from the blue line, like there's a little tiny distance here, there's a little distance here. If we measured those distances and added those numbers up, remember, distance from a point to a line is measured with a line perpendicular to the line you're looking at. So this would be the distance here. These there'd be little tiny distances. It looks like that measurement, the distance measurement, is minimized in line 2. If I were to add all these distances together, so there would be 1, 2, 3, 4, 5, 6, 7, 8 measures of distance. Okay, if I added those all together, then it looks like those distances are the least amount. That sum is the least amount for graph number 2. Now, if I look at graph number 1, it does go through 2 points. Notice that in graph number 2, the line actually doesn't go through any of the points. Okay. A line of best fit doesn't necessarily go through any of the points. It may go through some points, but it may not. In number 1, it does appear to go through 2 points, this one and this one. But if I start looking at the distances, okay, yes, the distance between these 2 points in the line is 0 because they're right on the line. But look at these distances. Okay, if I were to measure them in like centimeters or millimeters or feet or whatever unit, and I added up all these distances, this one, this one, this one, this one, this one, and this one, that measurement would be greater than in number 2. That same measurement in number 2. Again, we're talking about the sum of all the distances from the points to the line, right? These are 8 different sums we're looking at. In number 2, that sum is at the minimal amount that it can be. Okay. Another way of saying this is that the points in graph 2 appear to be close. More points appear to be closer to the line than in graph 1. Certainly in graph 1, these 2 points are close to the line because they're actually on the line. But the rest of the points do not appear to be as close to the line as they are in graph 2. And certainly in graph 3, yes, this point is on the line, but look at all these distances. If I were to measure the line segments that I'm creating right now, that measurement, if I add them all up together, would be much greater than the graph in line 2. So I would say that the line 2 is the line of best fit, where yes, these are both lines that go through one or more of the points, but they're not the line of best fit. It's the line that fits the data set, the data points the best. And we're going to talk about an algorithmic way to get this. Okay, so a common mistake, this should have said common mistake on the top. A very common mistake that people have is thinking that all graphs will cluster in a linear pattern. So it looks like the graph number 1 here has a linear pattern. So it looks like the line of best fit would be a line and not a curve. Okay, but in these other ones, it's actually better to fit these with a curve. Okay, so these other two, graph 2 and graph 3, there's not a line that would fit these the best. There's actually a curve. So if I drew a line like this, it's not, I wouldn't minimize the distances from the point to the line with that line. It actually minimize if I had like something that looks like kind of part of a parabola. And this next one too, this is like an S-shaped curve. That would actually minimize the distances because I might even be able to get all the points on the line if I did an S-shaped curve. And this is going to be, so it's these series of points in graph 3 are going to be modeled with an equation that looks like something like y is equal to x to the third. So any odd value of the exponent is going to give you an S-shaped curve. And the ones in number 2 is going to be something like y equals x squared because it looks like part of a parabola if you start looking at it. And anytime this exponent is an odd variable, or it's an odd number, you're going to get like a bowl or a parabola. Okay, so that would be x to the 4th, x to the 6th, and so on. Okay, so this is an example of a linear, so what I would do in your notes is I would sketch this down. A linear association would be something that could be fit with a line of best fit, whereas a nonlinear one would be fit with a curve. Okay, that's an example of a nonlinear, the length of a side of a square versus the area of a square. So let's look at the points here. This is definitely fit with a parabola because we know the relationship. If it's a square, we take all these numbers and we square them in order to get the area. Okay, right? If it's a if the square is 10 units, then the area is 100. If the square is 8 units, then the area is 64, and so on. If it's 5 units, it's 25, and so on. So this is actually half of a parabola. If I finish that up, it would go on that side. Okay, that's nonlinear. The height of a ball versus the time the ball was released. So if somebody at this height threw the ball up in the air, it goes up into a certain point and then it starts going down again. And this is actually another example of a scatter plot that would be best fit with a nonlinear or a curve. Okay, so it's a nonlinear association. It's fit best with a curve. And we're going to look at that. This is actually going to be fit by something like y equals negative x squared. So it looks like y equals x squared, but I have this negative sign in front of it, which means it turns it from this form shape to upside down to that shape. We're going to talk about that later on in the year. Now, let's say that we're trying to get a line of best fit for this information. Let's look at our data. This is the number of hours of sleep. So, of course, this is in hours. Versus test score, I'm going to assume this is in percents. Now, if I've already have a scatter plot and I'm trying to make a line of best fit, the first thing I want to do is I want to find the mean value of the hours and the mean value of the test scores. Okay, now in order to do that, I'm going to have to, usually I have this information in a table, but I don't have this information in a table, so I'm going to pause the video and put the information in a table. I'll just take them right off. I'm going to estimate from the graph and put it in a table. Okay, so I wrote everything down. I sort of chose one that wasn't the best because it had tons of points on it, but that's okay. I wrote all the information down. So for one, there's someone who had 1 hour of sleep and they scored a 61, and someone who had 1 hour of sleep and scored a 73, and so on. There's someone who got 10 hours of sleep and scored an 85, but for the most part it looks like there's a positive association here. Okay, again, so that we're looking at correlation, we're not necessarily saying that there's causation here. Okay, so it may be that they are associated, but one doesn't cause the other. Like the amount of sleep doesn't cause it looks like the more amount of sleep, the higher the test score, but it doesn't mean that the more hours of sleep causes a higher test score. Okay, to get a line of best fit, the first thing I want to do is take the average amount of hours. So to get the average amount of hours, I would add up all of these numbers in the left-hand column. Okay, so 1 plus 1 is 2. So you have 2, 4, 6, 9, 13, 17, 22, 27, and so on. And then I'm going to divide it by, I think I have 19 points. So I'm going to pause the video and do this real quick. Okay, so the average hours, so what I did was I added all these things together. I divided by 19. So the average hours ends up being it's about 5.37, okay? And the average test score was about 81.31. Okay, so I'm going to erase all the stuff for the table so that I can use this space to work. Now, the thing about this is I want to use this point as a point that the line goes through. So I want to use the point, let's see, the sleep is on the x-axis, so that's the x-coordinate here. I want to use this point. So let's plot that point. So it's about 5.3 or 5.4 and 81.3. So maybe it's about around here. So my line of best fit is going to go through there. Now usually I want to get a second point because I want the line to go through another point. So oftentimes if you have a situation where it goes through the point 0, 0, if you have a direct variation, then you can use that as a second point and line up, plot that point there and then draw the line through it. But it is not this. It does not appear that our data is saying that this is a direct variation. It appears that the y-intercept will be somewhere over here. Okay, so let's just pick a point that appears to be in the middle of a lot of these data points. So I'm going to pick maybe this point. I don't usually have to pick a point that's on the graph, but it appears that this point is sort of running through the middle. If I drew a line through these two red points, it would run through the middle of the data. So let me just informally draw this line right here. The second point that I picked was 372. Okay, so what I want to do is I want to take these 2 points. So this is my line of best fit, by the way. I just drew it. This line appears to fit the data pretty well. Now remember, that's the 8th grade standard, to be able to informally draw the line, and usually we use the average of these two, the information from the x and the information from the y, and that's a point that's pretty good for it to go through. Now sometimes the average is skewed by an outlier, so the thing that I just circled appears to be an outlier, like this one appears to be an outlier. Sometimes the line is skewed upward or downward, or the mean is skewed by an outlier, but it seems like we've just drawing it, it appears by our eye that it looks like it's a pretty good fit for these points. I can't really think of another line that would be a better fit. So if I'm trying to find the equation of the line, now this gets into our 9th grade material, because to find the equation of the line, we know how to do that using 2 points. So the points that I have here are these points. Okay, so let's find the slope of these points by subtracting. Okay, so I just subtracted those, and I'll let you use a calculator for these lessons because it's the data is not always it's usually not integer values. But remember that the slope is rise over run, so that's going to be 9.31 over 2.37. So I wrote x over y, but it's really the change in y over the change in x, or delta y over delta x. So it's 9.31 divided by 2.37, which arrives at about, let me round it to the nearest hundred, 3.93. Okay, so that's the slope, that's our m. Now to find our y-intercept, remember that we have to use, this is from like last week's lessons, we think of, so if this is our slope, we find the b by substituting, let's use 372. Let's say that, let's see, so if the y is 72, and that's equal to 3 times this value plus b. Okay, so 3 times 3.93 ends up being 11.79. And if I subtract 11.79 from 72, I would get 60.21. So our B appears to be 60.21. And so this line actually would go probably down something like this. Okay? So the equation of our line is y equals 3.93x plus 60.21. And rounding to the nearest hundredth is often a good idea for these lines, because you don't really want to round to the nearest tenth, because even a small rounding will affect the way that you can use the line to interpret the data. So we figured out what these things mean, right? We figured out the equation of the line. So we had y is equal to 3.93x plus 60.21. Now remember that the slope is how much the y changes when the x changes by 1. So remember, our y is how much so our slope can be interpreted as how much higher a test score can be. Or how much higher a test score is when you increase your sleep by an hour. And so when sleep is increased by an hour. Okay, so that's the interpretation of slope. And I'm going to ask you to do this, so please write this down. Now, the 60.21 is how much, so it's the y value when the x value is 0. Let's interpret that in our context. So it's the test score when sleep equals 0. So when there has been no sleep. When there is no sleep. Okay, that's what the x and y values are, the slope and the y-intercept are. Okay, the slope is how much the y increases when the x increases by 1. So I interpreted that in terms of our problem. And the y-intercept is how much there is on the y-axis when there's nothing on the x-axis. For us, is what the test score would be if there was no sleep. Now, is this accurate for you? Maybe not. You know, the point of having this line of best fit is we're taking in a lot of data points, and it may not be something that is good for one individual person, but it speaks to a pattern across a bunch of different people. Okay, so it's important that you understand that. Making a statistic doesn't necessarily mean that people are always going to, if I say that the average amount of time that people sleep is, 7 hours a night, that may not be, you make it more than 7, you make it less than 7, but we're taking information across a lot of different people, and we're taking the average of it. Okay? So this is how to interpret it. So what you learned today is you learned how to find the line of best fit using the mean of the x and y, and then another point on the line. We found the slope, and then we found the y-intercept using the point and the slope. We interpreted the slope and the y-intercept in the context of the problem. And that's the end of our lesson.